Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. We in Group 21 are going to present communication and computer network project that consists of two parts, which is part A and part B. Let's go to the part A, which is ARC protocol. Automatic repeat request protocols are error control mechanism in data communication to ensure reliable data transmission over unreliable networks. They detect retransmission by using acknowledgement, SEK, and timeout. The three main ARC protocols are stop and wait, go back and selective repeat. Let's start with stop and wait ARC. The most simplest ARC system, which is requires the sender to transmit one packet while waiting for acknowledgement before sending additional packet. Uh, there are two mechanics, sender and receiver. Sender sends a single packet with sequence number typically 0 and 1. Receive a packet, checks for errors and correct sequence number. If correct, sends an SEK with the next expected sequence number, delivers the packet to the application. The second ARC protocol is go back and ARC enables the sender to send many packets at once depending on window size before waiting for SEK, thus providing higher throughput than stop and wait. On sender mechanics, sends a packet within the window, each with a sequence number. On receiver end, if a packet arrives in sequence, deliver it, sends an SEK for the next expected sequence number. Uh, the last ARC protocol is selective repeat. The most efficient ARC protocol, which lets the sender send a multiple packet inside a window size before retransmitting only the lost or corrupted ones. Uh, let's start with the experimental setup and analysis for each scenario. Scenario 1, low packet loss and high bandwidth. The chosen parameter are 100 total packet. Packet loss and SEK loss probability is 1%. Network bandwidth is 1000 Mbps. Timeout interval is 5 millisecond. Network latency is 0.1 millisecond. Packet and SEK loss probability to replicate the theoretical network environment that experience very few packet and SEK loss, which is typical for top-tier wired network, including fiber optic LAN. Network bandwidth 1000 Mbps represent a high-speed network ideal for testing maximum throughput potential for the protocol. This is the chart for scenario 1 with three protocol arc have been tested on the scenario 1. Let's go for the analysis. Packet loss and SEK loss 1%. Low packet and SEK loss 1% reduce the retransmission, benefiting all ARC protocol. As for bandwidth 1000 Mbps, support high throughput, but stop and wait idle time limits the utilization because it need to wait acknowledgement before sending additional packet. As for go back and selective repeat can make an ideal throughput, but due to small window size, bandwidth is not fully saturated. Latency 0.1 millisecond, reduce round trip time, which is 0.1212 millisecond, minimizing idle time and timeout delays. Uh, as for timeout 5 milliseconds, it's much larger than round trip time, avoiding premature transmission but adding delay per loss. Based on the analysis that we have made, the best protocol is go back N because of the total transmission time is much lower than stop and wait and selective repeat, which is 0.029792 second. Throughput and bandwidth utilization is much higher than the other protocol, which is 403.8061 Mbps and 40% of bandwidth utilization. Uh, because of the throughput and bandwidth utilization is much higher, the processing overhead is lower than the other protocol, which is 1.46672%. That's all. That is my part. Thank you.
Alright, we move on to experimental setup. For this experiment, we test three RRQ protocol, which is stop and wait, go back and selective repeat, under various network conditions to evaluate their performance and reliability. We adjust several key parameters for each test case, with the packet loss probability range from 1% to 50%. ACK loss probability was set between 1% and 15%. Network bandwidth varied from low at 10 Mbps to very high up to 1000 Mbps. We also consider latency, keep it at either 0.1 millisecond or 10 millisecond, depending on the scenario. Timeout interval were set at 5 millisecond to 10 or 10 millisecond. For go back and selective repeat, we test two window size, which is 4 and 8, to see how that impact throughput and retransmission. We designed four main scenarios to reflect realistic networking environment. The first one is the ideal network scenario with low packet loss and high bandwidth, help us establish baseline performance for each protocol. Second, a congested network with high packet loss and low bandwidth, test how protocol handle heavy retransmission and errors. And the third one, we stimulate a high latency network with two different timeout values to examine effect of timeout turning on performance. Lastly, we explore the impact of window size by testing go back and selective repeat with window size of 4 and 8 under moderate loss and delay. This configuration allows us to analyze the strength and limitation of each protocol across varying conditions, from ideal to challenging.
Hello. Alright, so in scenario 4, we will investigate the impact of window size on protocol performance, focusing specifically on go back and selective repeat ARQ, since stop and wait does not utilize a window-based transmission. Right, looking at the graphs right here, looking at what we've done, the data, the condition of this scenario simulate a moderately lossy network with 20% packet loss, right? 50% ACK loss, 100 Mbps bandwidth, 0.1 ms latency, 5 ms timeout, and also window size of 4 and 8, right? These settings are ideal for analyzing how pipeline ARQ protocols respond to both loss and window limitations in a relatively fast but unstable network environment, right? Looking at the graph right here, let's break down what the results show us. So, for go back and ARQ, the retransmission count rises significantly, 43.6 packets, because a single lost packet causes the protocol to retransmit all subsequent packets in the current window. This pushes the total number of packets sent up to 266.2. Despite the inefficiency, go back and still achieves a decent throughput of 81.24 Mbps thanks to the high bandwidth available. Its processing overhead remains moderate at 16.17%. On the other hand, selective repeat ARQ handles losses with much more precision by retransmitting only the individual packets that were lost. It limits its retransmission to 33.4 packets, a significant reduction compared to go back N. This means fewer wasted transmission, with only 133.4 packets sent in total. As a result, selective repeat achieves a higher throughput of 93.98 Mbps, although its processing overhead is slightly higher at 25.1% due to the complexity of tracking and buffering out of order packets. Right. In essence, while go back N leverages pipelining for improved performance over stop and wait, its full window retransmission strategy becomes a liability when packet loss increases. Selective repeat, although more complex, clearly handles the window environment more gracefully by recovering from errors with minimal excess. Key insight from scenario 4. Right. This scenario highlights a crucial network trade-off. Right? A larger window increases throughput potential by allowing more packets in flight. But if the retransmission strategy is inefficient, as seen in go back N, it can lead to significant bandwidth waste. Right. Selective repeat while demanding more processing and buffer management, proves the fine-grained error control paired with pipelining is the optimal balance between reliable and speed, especially in networks with both high bandwidth and noticeable packet loss. Okay, a well-sized window with selective repeat can help achieve near ideal throughput without flooding the channel with unnecessary retransmission. Alright, through the detailed evaluation of all four scenarios, it is evident that selective repeat ARQ consistently outperforms both stop and wait and also go back and ARQ across the various network conditions, making it the most reliable and efficient choices in real-world applications. In scenario 1, low loss, high bandwidth, low latency, all protocol benefits from minimal retransmission, but go backend excels due to its lower processing overhead and faster total transmission time. Looking at the graph here, its window-based pipelining helps it utilize bandwidth efficiently without the added complexity of buffering. Right, so in scenario 2, right. In scenario 2, high packet loss, low bandwidth, selective repeat clearly dominates. Its ability to selectively retransmit only lost packets dramatically reduces overhead, which is critical in low bandwidth environment. It maximizes throughput and bandwidth utilization despite heavy loss, showing its resilience. Right, so for scenario 3 here, right. Scenario 3 introduces high latency with varying timeout intervals. Here, selective repeat again proves superior as it mitigates the effects of premature timeouts through its selective retransmission and buffering strategy. While both 5ms and 5 and 10ms timeouts are shorter than the RTT, selective repeat minimizes the performance penalty better than the others. And finally, scenario 4, right. Varying windows sizes under 20% packet loss and 15% SCK loss. Selective repeat demonstrates its scalability. As the window sizes increase, it maintains high throughput up to 120.848 Mbps with significantly lower retransmission and overhead compared to go back N, which suffers from window-wide retransmission. Selective repeat effectively balances high performance and low waste, regardless of window size. Right. Selective repeat ARQ is the best performing protocol in scenarios 2, 3, and 4. Its strength lies in handling losses efficiently with selective retransmission, utilizing receiver buffering for out-of-order packets, and consistently maintaining high throughput and bandwidth usage. Meanwhile, go back N ARQ shines in scenario 1, where its simplicity, lower processing overhead, and speed makes it ideal for clean and high-speed network. For the final verdict, selective repeat ARQ is the most robust and versatile protocol, excelling in environments with high packet or SCK loss, limited bandwidth, long latency, and dynamic or large window sizes. It's designed to adapt, survive, and thrive. And while Go Back N holds its own in optimal condition, it simply can't match the efficiency and resilience of selective repeat under challenging circumstances. So, in real-world setting where unpredictability is the norm, selective repeat is the safest and strongest bet for ensuring data reliability, speed, and minimal resource wastage. Right. Thank you.
Alright, so let's move on to our part B, which is our computer network design. Alright, so in our objective, it is mentioned that we need to design a practical and cost-effective network solution for Narmi Sedia Berhad. So, what are the requirements that need to be satisfied for the network diagram? One, it is the one internet gateway from ISP, which is 500 megabits per second downlink and 300 megabits per second uplink, which is shared between two offices, that is Office A and Office B. And there are employees count that we need to consider, which is in Office A, there are 15 stationary employees and 5 mobile employees. Whereas for Office B, there are 10 stationary employees and 3 mobile employees. For printers, in Office A, there are 2 printers in that specific location. Whereas in Office B, there are 1 printer that needs to be inserted in there. Now, let's go to the meeting rooms in both office. Both of them required restricted Wi-Fi access for the incoming guests. Alright, so if we move on to our next slide. Now, this is our proposed network diagram. As you can see, it is fulfilling the criteria that is needed based on our previous slide. So, as you can see in this container, which is containing at least 1 stationary employees, and for this it is main for mobile employees, and for this one it is main for the meeting room. Now this applies the same case for Office B at level 2. However, the difference is the number of printers and the number of stationary employees and the number of mobile employees that is connected to the switch. Now, as we can see here, in Office A, it is connected to Office B switch via wireless links, therefore through wireless bridge. Now, this bridge allows wired links to be converted into wireless link and allowing the connection to be distributed to another switch, which is required to use another wireless bridge. So we will explain why we use this particular wireless connection between two switches. Alright, so let's talk about our network technology and justification. Now the type of topology that we use to create this diagram is a tree topology. Now the benefits of using this topology is that it is having an efficient data transfer, which is to reduce congestion and better bandwidth. Other than that, it has point-to-point connection, which offers dedicated bandwidth. Next of all, it is reliability, which is to isolate the errors within the network without affecting the root node. So no matter what errors that cause on the other nodes, maybe the leaves of that tree topology, it does not affect the root, which is the router itself. So for security, it is to enhance the privacy and security via dedicated channels. As you can see, I have mentioned that why did we use wireless link for Office A and Office B? Now, the reason is that it provides better mobility than wired links. Now, wireless link has easy setup, which indicates quick installation and cost-effective rather than implementing string cables. Lastly, wireless links are reduced in cost than wired links because wireless links eliminates the needs for wiring expenses which cost less to operate. If we move to the next slide, now let's go to our meeting rooms. These rooms uses restricted Wi-Fi access, as I said before, for guests. Now we use firewalls to implement any of our Wi-Fi access. So this firewall is used to prevent any malicious activity and third party to try to steal guest credentials. Now, for our stationary connection, now this connection in Office A and Office B implements star topology, which indicates that these devices will connect to the switches via internal cables. The benefits is that it has easy fault detection because the links are often easily identified if it's causing problems other than the hub. Now, it is less expensive because each device only requires one I/O port and uses one link to connect to the hub. And lastly, it is high performing as no data collisions can occur. Next is our mobile connections. Now, these connections in Office A and Office B implement star topology. as well as we mentioned in our previous slide, which is the stationary connection. So the benefits is a bit similar, but in terms of the cost. Now, for it has high robustness, which means that the connection of the devices is strong and will not face much problem than wired ones. And it is less expensive because no cable are required to connect from the devices to the switches via wireless access point, or in short, AP. Now, it will increase in bandwidth for the devices connected to the wireless AP.
Okay, we'll continue with the component justification. First, the router. We will connect the both office to share internet gateway. We will use around 500 Mbps or 300 Mbps that support bandwidth management to prioritize internet traffic and gas station. So, and then we provide network address, translation, and basic firewall for the protection. And then for the switches, we will use it in the star topology to connect all stationary device. And then each office will get 24 gigabit switch to support current and feature expansion. And then it will also support VLAN configuration for separating internal and guest traffic. For the wireless access point, the APS, we will use the dual band APs installed in the office and meeting rooms. Next, for the capacity planning, the internet bandwidth allocation, we will use, as just I said just now, the 500 Mbps downlink and 300 Mbps uplink shared between both office. So this traffic shaping ensure critical services, just like the cloud apps, file sharing, to get the priority. For the scalability consideration, all the switches and APs chosen to support future growth, which means to support more employees and more device for the future. For the security measures, the firewall rules and VLAN segmentation for isolating guest traffic, restricted SSID access for the meeting room, and then all printers on internal VLAN will not accessible to the guests. And then this is the specific for this project. The Office A capacity planning, it will has 15 stationary and 5 mobile users, which is connected to gigabit switch and 2 APs, 2 printers shared over the LAN, 1 AP placed in the meeting room for restricted guest access. And then for the Office B, it will has 10 stationary and 3 mobile users connected to the gigabit switch, and then 1 to 2 APs. It will also has 1 shared printer and 1 AP for meeting room guest Wi-Fi. So in conclusion, we successfully designed a cost-effective and practical network for NAMI Sdn Bhd. The network meets all the requirements, ensures strong security firewalls, VLAN and guest Wi-Fi restriction, and delivers high performance with efficient bandwidth use. We also use a hybrid topology, which is the tree and the star, to balance performance, reliability, and security. Offices are rolling wirelessly for flexibility, while wired connection provides stable access for stationary user. Finally, we selected suitable hardware and planned capacity to support both current operation and future expansion. I think that's all from us. Thank you.